Ready? Now, in order the beans meet the pickles, right? I mean, we got an electrical engineering circuits 1 problem, okay, where we are asked to find a current and a voltage. We are given this circuit here, yeah, I mean, let's go ahead and analyze it. All right, let's go ahead and work on it for a little bit. Okay. All right. So. Alrighty, so okay, so let's see how this circuit is wired up. We got a current source right here. Okay, direction of the current going up. We have a resistor of 2 ohms. Okay. And it's wired up in such a way that the negative is on the top and the positive is on the bottom. Then we have the current source the current that we're trying to find, which is over here. Okay, like right at this node here, where it divides off into other sides, but we want to find this current on this specific branch here before it enters the resistor. We have a voltage controlled current source, okay, and it's telling us that it will reduce the current. Whatever this current is, it's going to reduce it down to 25% of it once it comes out, and it's going to be pointing in this direction. And lastly, we have a resistor here that is of 8 ohms, and we want to find the voltage across this resistor. And we see that it's wired up in such a way where the positive's at the top and the negative's at the bottom. Okay. So, all right. So the first step is to do a nodal analysis. Yeah, use a KCL analysis, Kirchhoff's current law analysis. Okay, so let's start with KCL. Okay, KCL analysis. I'm going to hover off to the side over here. So if I'm floating head in the corner of the video. Okay, so yeah, so we have our KCL analysis section. So we're going to look at this circuit, and we're going to see that there are. We're going to look at the top here. Okay, there's 2 nodes. Okay, there's one node here. There's another node right here. All right, so we're going to name them. We're going to be like node A and node B. Okay, these points of intersection here. All right, and we are going to draw the first node. Draw A. Okay. All right. Okay, so we know that we have 9 amps going across from this side. Okay. All right, 9 amps. And we know that the current is going to essentially come out of this side, and it's going to go down over here. Question is, we don't know the current. Like once it hits that node point, we don't know how's it going to separate. The thing is that at this other node, at node B, we have a voltage controlled current source. So the way to look at this is that, okay, let's do our other node, okay? All right, so okay, so the way to imagine it is that we have this voltage controlled current source here, and this thing is going to do 0.25 IO. By the time the current reaches this point here, there must be at least whatever quantity of current there is here, there must be that coursing through this line, okay, in order for it to then take the 25% of it. So this entails that it's going to be, it's going to be drawing, once it reaches this line, it's going to be drawing whatever this quantity is. But when they get separated out, okay, each line is going to be drawing half of this current, okay, half of this current, okay. That's the way to think about it that works for me. So we have I0 over 2, which is half of I0. And then on this side, we have I0 half of I0. And when they come together on this point here, on this node, they become whole and become I0. And this makes it so that once they pass through this voltage control current component here, it's able to have that initial condition of like I0 in order for it to then take the 25% of it and then spew out the 25% of I0. So because these lines are connected here, we can just say that the current that's being pulled, okay, across this line up here is going to be I0 over 2, half of I0. And okay, so there being said, when you use Kirchhoff's current laws to examine one node at a time, what you need is, of course, you need one node, okay? You need some value of its outputs, and you need to know how much current is going in and how much current is going out, okay? And if you know that, then you can then all of it combined will equal to 0, okay? And this comes from some conservation of energy physics type law, where the combined inputs and outputs of energy are going to ultimately be 0. Okay, so you have 9A. Okay, so we add to the node, we add the currents that are going in, okay, and then we subtract the currents that are coming out. So half of I0 is going out, and then I0 itself is also going out. I0 over 2, okay? Let me make sure I'm keeping track of my notes here. Okay, so in order to find what I0 is, we now do algebra, okay? We do algebra. So, okay, I'm going to start out, I'm not going to isolate I0 because we have to factor I0 out of this group here. So we're going to move 9A to the other side of the equation. Okay, we're going to subtract it out. Okay, there, okay, and you bring it to this side. And now we're left with negative I naught minus I naught over 2, okay? Pardon me if this looks like a J, but, you know, after being in physics for long enough, you kind of got to make sure to, like, your eyes look different than your J's. That's from doing a lot of vector stuff, but I digress. Okay. Am I recording? Yeah, I am. All right, so now we factor the I naught out of this expression here, this side of the expression. So both I naughts are negative. Okay, we have these two elements share negative values, and they also share the I naught. So we can proceed to factor it out. If we take an I naught out of this element here, we're left with 1. Okay, I naught times 1 is equal to I naught. And then, because we've taken the negative out of there, we can make this whole this element here, we can make it a positive. We've taken the I naught out of it, so we're left with 1/2. Okay. There you go. And now we can just algebraically move this parentheses out of here and bring it over here. So here's what we're going to do. We're going to do that. Okay. 2. All right, that comes out of there, and we chuck it over here. All right. There we go. And yep. And now we're purely left with just negative I naught. So the way we can get rid of this negative is by dividing it out as well. So, all right, we have an entire expression there. We take this I naught, we divide it. Okay, there you go. And because this is a -1 per se, we can just say that whatever this element is, this expression is going to be, it's going to be negative. So we can just say, we can pull the negative up top here. And there we go. I naught is equal to this expression here times -1. So let's pull up the calculator, see what we get. Okay. -9 over parentheses 1 plus 1/2. And we get that I naught is equal to 6. Okay. There you go. So that is our first part of the problem, figuring out what I naught is. So we're gonna go up here, take the question sign out, and now we know it's equal to 6 amps. Okay. That is the unit of current. Okay. Let me clear up the board again. Clear up the board. If you haven't taken any notes or anything, you can just pause the video and at a previous time and take notes. Okay. So what we did was KCL analysis. Stands for Kirchhoff's current law analysis, where you look at a node and you look at the input and output currents. You add up the currents that are being input to the node, and you subtract out the currents that are being output the node. Now we have to find what VO is. Okay, so there's a thing called mesh analysis, where you can look at one loop at a time. Okay. You can look at a loop at a time when it comes to these parallel wired circuits. So VO is on this last loop here, okay? And this negative, the 0.25 IO, we know what IO is, so we can now substitute in for IO and get the actual value that our voltage-controlled current source is going to be outputting. So, all right. All right, so 0.25 times 6, right? Let me do the math real quick. It's going to be 0.25 times 6. It's going to be 1.5. Okay, so the output of this voltage control current source is going to be 1.5 amps. Okay. So here's what we're going to do. Okay. Doing loop by loop analysis, we can see that that the voltage coming out this way. Okay. No, not the voltage, the current. Okay. And it's going to enter into the negative part of our resistor. Okay. So yeah, I mean, current likes to flow from. It'll flow in any polarity. It's just say if you had a current source that was outputting current up, it would flow around. I mean, but the polarity of your resistor, because it's not entering at a negative part of the resistor, it would output a negative voltage. When you measure it, okay, when you measure the voltage, the potential difference across the resistor, okay. But I mean, the engineer that wired this up did all right. I mean, because since the current is going downward and it's going into the resistor through the negative through the negative terminal of it, that means that the calculation that we're going to do here, it's going to end up being a positive. So the voltage or the God, I mentioned it. Electric potential? No. Yes. The electric potential, or in other words, the voltage across this resistor, because it's the current's coming out. It's coming out of this way and going into it through its negative terminal. We should get a positive. So positive calculation. The polarities are right. Okay, so what we're going to do, Kirchhoff's voltage laws, okay, KVL analysis, and let's see. Actually, we might not even need to do KVL for this. We can just do. Let me just make sure. Yeah, we don't really need to do Kirchhoff's voltage laws for these. We can just use Ohm's law, which states that voltage is equal to current times resistance. Okay. We have a current. Our current is, again, 1.5 amps. Okay. And we have a resistance. We have, the resistor is 8 ohms. Okay. And so our voltage should be 1.5 times 8, which is 12 volts. Okay. Therefore, V naught is equal to 12 volts. All right. Okay, so we're good on 20 minutes. Alrighty. Yeah, these types of problems aren't too crazy, but they're interesting to get a grasp of, you know. And alrighty. Yeah, I think this is a fantastic example of using Kirchhoff's current laws and Ohm's law to solve some of the parts of this circuit. I think I might do more of these circuits videos. I think they're pretty fun. Alrighty, yeah, those are the answers. And yeah, good luck. If you watched this far, hit a like and subscribe. Okay. Share it around. Yeah, Godspeed.